Welcome back. In this episode, I'm going to be talking about libraries and the specific library, NLTK, which stands for the Natural Language Toolkit. If we look in 16's library, I've provided a few different libraries that are actually quite useful. Now, a library is essentially a module that contains a lot of extra code that's not loaded into the default namespace. So some of these are part of the standard Python distribution, like math and random. And to use them, we have to import them. Now, this happens because you don't necessarily want to pollute your namespace with a lot of extra things that you're not going to be using. So if I want to use some useful math functions like logarithms, I can import math. If I want to be able to create random numbers or pseudo-random numbers, I can import the random library. If I want to use the regular expression library, which we'll see later, I import RE. If I want to interact with my operating system, I can import the OS library. And if I want to deal with JSON objects, which we'll see when we talk a little bit about web scraping, I can import JSON. For the sake of what we're doing today, we're going to be, in this episode, we're going to be using libraries that are not part of the standard Anaconda distribution. You can actually, let's back up to where I just finished talking about JSON. You can actually find all of the libraries that come with the standard distribution of Python if you go to docs.python.org and look at the libraries. Now, Anaconda, and this is why we're using Anaconda specifically, contains a lot of additional libraries that we're going to be using. For example, there's the Natural Language Toolkit, which is the focus of this episode. There's matplotlib, which we'll see in data visualization. Pandas, which we'll see in data munging and a little bit in visualization. There's NumPy, which is the numbers Python library. If you go to docs.anaconda.com, you can find a list of all of the libraries that come with Anaconda there. And in some cases, you might have to install them separately, which is fine. You can actually import these libraries with aliases to help yourself out a little bit and not have to type so much. For example, when you use pandas, you can import pandas as PD. That way, when you use pandas, you don't have to type pandas over and over again. You can also import individual modules from libraries, because sometimes you don't need the whole thing. So for example, from matplotlib, I can import pyplot by itself. I can also say from matplotlib, import pyplot as PLT. This is just importing the pyplot module from matplotlib and using an alias for it. What you'll more often see is from matplotlib.pyplot import PLT. Okay? So that's really what I wanted to say about libraries in general. I want to now talk a little bit about NLTK specifically. Now, this is a library that contains a lot of functions that are very useful in the context of the digital humanities and in linguistics in general. You can find a lot of very useful exercises and much of the information on which I'm basing my lessons at the NLTK.org book website, and some of my tutorial comes from there. So the first time you use NLTK, and you'll only need to do this once, you'll need to download a few extra files because it doesn't come with all of the functionality right out of the box. The first thing you need to do is you always have to import the library before you can use anything in it. And then from there, what you'll need to do is you'll need to call nltk.download, open parentheses, close parentheses. When you run this code, it's going to open up a window, and from there you can choose what you want to download. Now, what I'm going to do is I'll run this, 17 nltk1.py, and what it's going to do is, because I'm in full screen, I'm going to back out here, and we're going to see here that it opens a window called NLTK Downloader. There are all sorts of things you can install. For the sake of this class, you're only going to need Popular. If you're using the computers in the computer lab at Leiden, it's best to do this instead of all, because all is a lot of data and it can really slow down your account. So I recommend sticking just with this. But you'll click download, and once it's downloaded, you can go ahead and close this, and then you're done. Now note that your code will not stop running until you close that box, so just be aware of that. And now once we've done that, we don't need to do it again, and we can start moving in to talk about the Natural Language Toolkit itself. Now, the Natural Language Toolkit contains a lot of tools that are going to be very useful for us as part of this class. we can actually do both the sentence and the string tokenization all in one go. I can create a dummy list to contain all of my results, and I'm just going to call this sentence word tokens. And then the first thing I'm going to do is I'm going to break the document into individual sentences. So I'm going to say nltk.sentTokenize home string, and I'll save that as this sentences variable. And then what I'm going to do is I'm going to break each of these sentences into individual words. So using a for loop, I'm going to say for every sentence in this sentences list, use the word tokenize function. So nltk.wordTokenize, and then stick the sentence in there. This will tokenize the sentence into individual words. And then what I can do is I'll take that tokenized sentence and I'll just append it back onto this sentences words tokens list. And here, I can then print the 1000th sentence. And if I do that, what we see, I'll just run this code, that in fact, it gives me the sentence, "To smoke," he answered. And you can see that that is from our last code, that 1000th sentence, but now it's broken apart into individual tokens for the words, which is a really useful thing to do. Now you'll notice it's printed twice because I actually wrote this twice. We can actually use what are known as list comprehensions to condense that for loop into a single line. This might look a little weird, but we'll see it a few times throughout this course, and hopefully it will start to make more and more sense. So what I'm doing is I'm saying nltk.wordTokenize sentence for sentence in nltk.sentenceTokenize home string. So this is a little odd, but what it's doing is it's saying for sentence in nltk.sentenceTokenize home string. We've seen this. This is just a regular for loop. But we can actually then use this sentence, which is a variable name we've created, and use it here, and then call this nltk.wordTokenize on that sentence. So we can condense it all into a single line. But if that's a little confusing, that's fine. You can just use this more verbose way. It'll run just as fast. Or, well, technically that might not be true. List comprehensions might be slightly faster. But I'd have to double check that. So once we've learned a little bit about how we do these tokenizations, we can start to think about some of the larger functions that NLTK will give us. NLTK actually comes with an object type that has a lot of very useful methods that will facilitate most of the very common tasks we'll want to do. We already saw how we can build a word frequency piece of code ourselves. NLTK has functions that make that very, very easy. So here, all of this code is just exactly the same as before. But what I'm going to do now is I'm just going to tokenize this into words. I'm not going to deal with the sentence tokenizer. If I give this word list to the nltk.text with a capital T function, it will create a text object. And this is very, very handy because it comes with some cool functions, or methods. So the difference between a method and a function is that a method is attached to an object, and a function exists independently of it. So we can actually create concordances with this text object by just calling the concordance method and giving it the word Holmes to see what's happening around Holmes. I'll print this, or I'll run this, excuse me. This is NLTK 3.1. Let's run that. What we can see is it'll do the processing, and then it'll give us this concordance, which is, we'll make that slightly smaller. There we go. So we can see that it found Holmes everywhere, and then it found all of the words on either side of Holmes. You'll notice that this is not actually case sensitive, which is nice, but often it's better to adjust for that ourselves anyway. So if you want to kind of adjust the appearance of this, you can actually adjust the width, that is how many characters on either side of Holmes are being displayed, and how many instances are being displayed. So you can kind of play with this to see different views of your data. And this is an effective way of finding how are certain words being used in the context of a document. So if we look at some of the other things that this text object makes available, we can see, I'm just going down here. This is all the same, nothing new here. But if we want to, for example, find similar words, that is, words that show up in similar contexts, We can use the .similar method. Giving it apartment will show us words that are used in similar contexts to apartments. We can create a dispersion plot by giving it a list of words. And what a dispersion plot is it just shows us a plot of the entire text and where time is kind of delimited by each character, and we get a slash every time the word murder or death shows up. It's a pretty handy way of seeing how words are distributed across a document. We can get collocations, which are words that seem to be related to each other by virtue of showing up in similar contexts. And we can also get word frequencies. Of course, we could do this ourselves, but NLTK has some handy ways of doing this. And we can also get the most common words using a most common method. There's also this fun method called hapaxes, which show you words that occur only a single time. But I'll run this code, and we can kind of see what these various things do. And this will open a new window because that dispersion plot does create a new window here that has murder, and it gives you what the word offset, excuse me, I said character, it's the word offset. So how deep into the text does that show up? So you can see that the second half of this collection of documents, the Adventures of Sherlock Holmes, actually doesn't contain the word murder, although this is case specific, so maybe it includes the word with a capital M. I don't know. So we'll close this, and the code will continue to run. And we can see words similar to apartment, room, house, street, door. Those make sense. Some of the others don't make quite as much sense. But this similar method will work much better on a larger corpus. Here we can see Sherlock Holmes occurs together, said and Holmes, Mr. Holmes, Miss Hunter, Scotland Yard. These things all make quite a bit of sense. We can actually now use NLTK to do a few types of basic analysis. So let's do a quick analysis of this set of documents. So here, I'm just going to go through and do the same things all the way up to creating this tokenized list of words. The next thing I want to do is I might want to filter these words. So I want to remove punctuation, and I want to make it lowercase. So what I do is I just go for every word in this word list. I'll check, is it alphanumeric? And if it's not, ignore it. Otherwise, append it to the filtered words, but also make it lowercase. Now, we could do this all in a single line. So filtered words equals word.lower for word and words if word is alnum. Understand that this does the same thing, and try to get a feel for this, because it's a useful and quick way of building code. Now what we can do is we can check to make sure that everything's lowercase and no punctuation remains by looking at the first 25 filtered words. And then we can check the total number of words in the document. This is a useful thing to do. And I'm just going to print, the Adventure of Sherlock Holmes contains length words. Now we can also get the number of unique words by using the set method, or excuse me, the set function, by saying set filtered words equals unique words. We've seen this before. And we can get the total number of these unique words by checking the length of the set. And then we can say, of however many words, X number of words are unique. And using this, we can calculate the lexical diversity. And this is a very interesting metric that can tell us a few things about a document, but what it actually does is it tells us, for every unique word, how many total words are there? So I just divide unique word length divided by length, and this is the lexical diversity. And this is actually a real metric that people use in the context of analysis. Often it doesn't tell us as much as we might want it to, but that's neither here nor there. We'll talk more about that in the actual class. So I'll run this NLTK 4, and we can see that the Adventures of Sherlock Holmes contains 103,000 words. Of those words, 7,677 of them are unique, and it has a lexical diversity of 0.0745. So about 7% of the words are unique. So this is a pretty useful thing to know. Now, we might want to actually refine this even further. Now, you'll notice that when we did this, what we're doing is we're treating certain words as exactly the same. Running and runs are the same. Hunt and hunts would be the same. We might not necessarily want that. So we might want to actually do what's known as stemming. That is, chop off the endings of words so we don't get that variation. So the prep is exactly the same as before, and I've gotten back to my filtered words list. To get rid of all of those word endings that we might not want, we can use the snowball stemmer, which comes with NLTK, and this is part of the reason why we needed to download those extra things, because it's not just with the regular package. We can specify the language, and there are other languages available. And I'm going to save this as a stemmer object. So we're just creating this object that we're then going to use. Now, I'm going to start with an empty list, and then I'm going to go through every word in that filtered words list, and I'm going to append the word after I have put it through this stemmer. So I'm going to use the stemmer.stem word. So this is a little bit, we're building things together, but this will chop off the ends of all of my words and just save it in this stemmed words list. And we'll take a look at what that looks like. Now, a problem with using this stemmer is that it will produce words that are not real. We might want to avoid this. We can do that with what is known as a lemmatizer. Lemmatization is like stemming, except it also makes sure that the stemmed word is a real word. So there is a WordNet lemmatizer that comes with the Natural Language Toolkit, and we create an object just like we did with the stemmer, and then we can say lemmas equal lemmafinder.lemmatize word for word and filtered words. And this is doing the same thing, only instead of stemming it, we're lemmatizing it. We'll print out those lemmas, and we can see what the difference looks like. So Python NLTK 5, stemming, and we'll run this. Now, the reason you might stem and not lemmatize is that lemmatizing is significantly slower than just stemming, although it is much, much better in terms of the results you get. So it's kind of a trade-off. So here we can see the stemmed words. We can see that for some of them, it looks just normal, but in some cases, it doesn't. So adventure, it cut off the E. Home, it cut off the ES, produce, anonym. So it's cut off these words, but it hasn't made sure they're real. In the lemma list, though, we now see that it has homes, it has produced, it has anonymous, it has Sherlock. It has actually made these lemmas and made sure that the results are still the same. So this is a very useful thing if you want to do word counts and you don't want to treat plurals different than singulars. So with that, that's the very basics of using the Natural Language Toolkit. We'll see it more as we move on through this course in conjunction with plotting libraries and other data analyses to do even more complex things. In the next episode, I'm going to talk about one of the most critical concepts in all of computer science, and that is regular expressions. And I hope you're excited for it, and I'll see you in the next episode. Thank you.